as we take a look at logarithms, basically what they are is they're the inverse of the growth functions that we just got done with. So what we're going to do is we're going to look at them algebraically and graphically to kind of see how some of these things work, where we can come up with values. When you're thinking about applications, without logarithms, you would not have the cell phones that you live on, some of you. So, you know, something to actually give you a little incentive to learn how these things work. So when we're rewriting logs, and I kind of get myself in a little bit of a rhythm when I start doing these, I'm like, okay, how can I see how these things are similar? So when I'm trying to go from a log to an exponent, or an exponent to a log, how I can keep it straight. And here's basically what I do. When I'm doing an exponent or a log here, that b value is called the base, and that's what I'm going to keep referring to it as. So I always look at this as, oh, if I'm looking for similarities, my base, exponent, solution. Base, exponent, solution. So like if I'm looking at this, my base is always going to be that little subscript that's down there, the little itty bitty either variable or number that's there. My exponent will always be on the other side of the equals, so I just call it my answer. And then my solution. And if I wanted to find the answer, I could. I could take both sides to the 1/5 power, do an opposite to do that. But right now we're just rewriting them. So no worries as far as that goes. Again, so a little subscript is going to be my base. My solution is going to be my exponent. And that's my answer. You're like, well, hey, 5 to the 0 is 1. They will always make true statements. So if you ever write one, you're like, well, wait a minute. I've got 5 to the first equals 0. That doesn't make sense. It kind of helps give you that little bit of guidance. So what do you think number 3 would look like? So 10 to the first equals 10. Base, exponent, answer. 10 to the first does equal 10. Okay, that makes sense. What about on 4? Ten to the negative 1 equals 0.1. Now, you may look at that at first and go, I don't know, is that right? Well, let's see. And I'm also going to show you how it may be written as a fraction, and that may make a little more sense here. So 10 to the negative 1. Yeah, that's 0.1. But wait a minute, 0.1. Oh yeah, that's 1/10. So let me look at it this way and see if this makes more sense. Oh yeah, 10 to the negative 1. When I have a negative exponent, remember that doesn't make the answer negative. It means I take it and I flip it. I take its reciprocal. The 10 goes down to the bottom. Oh, okay, this makes sense. I get it. So when there's numbers everywhere, it makes it a little bit easier for us to see if it's going well or not. So let's see here. What about 5? Then we start to get abstract. What would 5 look like as an exponential? Half to the negative 1 equals 2. Now think about that for a second. Half to the negative 1 means I flip this. What happens when you flip 1/2? 2 over 1, it's 2. Okay? So it kind of lets me practice my exponent rules a little while I'm using these new items called logarithms. And we can actually do these in the calculator too, but we'll get to that. You're like, well, wait a minute, what about these next ones? There's nothing here. Okay? Typically, if you get something like this, I like to refer to the equals part as x because that's what I'm trying to figure out. So you're like, okay, so b to the x equals 1. Now, what if I ask you to actually figure out what x equals? Oh, geez. You're like, wait a minute, that's a variable, that's a number. Anything to the what power equals 1? 0. Nicely played. Whether it's a variable or an exponent, if you take anything to the 0 power, it equals 1. So it just kind of lets me use that rule in general. You're like, ooh. Number 7. Okay, what's that going to look like as an exponential? Then we'll figure it out. b to the x equals b. b to what power gets me b back? 1. Looks so complicated, but it's really not bad once you kind of start getting the hang of things and start getting these in there a bit. So you're like, okay, so evaluating. Well, wait a minute, what's that mean? There's 2 ways I can do this. I'm going to show you both, but there is going to be a time that I have you do it without a calculator. So I'm just warning you in advance. We're going to try it first without it. On these, every one of these, if I don't have an equals sign, I'm just going to put an equals x in here for the time being. So here's how this works. Still going to write it as an exponential. But here's where I may have to play a little bit. I'm not going to be mean and start turning these into fractions and weird things like that. But I am going to make you think a little bit. So here I need to figure out 3 to what power gets me to 81. Any ideas? It is a whole number. 4, I'm being told. Yes. Okay, so my x is 4. We just started kind of playing with it in our minds here on how this might work. Now, these will kind of start getting tricky. Now, the decimal, I don't like decimals. I'm going to turn that decimal into a fraction here in just a second. Okay. So this is log 5, 125 equals x. You're like, well, that really didn't help, Harty. Seriously? So you're telling me that I should do 5 to the x power equals 1/25th, and I should know this. Kind of. Let's think about what we were doing up top a couple of times, and let's make life a little simpler on ourselves. 5 to what power is 25? 2. Okay. But this doesn't say 25, it says 1 over 25. So if I want it flipped, I make it a negative exponent, because 5 to the negative, oops, no, not 5 to the third. 5 to the negative second is 0.04 1/25th. So again, if you've got a firm foundation already with your exponents, not too bad with your powers, with your squares and cubes and stuff like that. Otherwise, this can get a little interesting. But again, I'm going to show you a way to play with it in another way here in just a minute. When you see the fraction to a whole number, or a whole number to a fraction, you're going to have a negative exponent involved. So I know I'm going to have negative something. 2 to what power gets me to 8? Oh, I'm frightened. I'm going to start writing notes in here already. It's 3. Flashback. We're finding that out right now. Yes. You still have to have a grip on squares and cubes. Squares probably to 10, cubes at least to like 5, I would say. Now again, you can just play with the calculator. You can, but I'm going to be asking you to show me some different things. And like I said, I'm even going to show you a way to do some things in the calculator, which I know some of you are going to jump into crutch mode with. But we'll make it okay. All right, one last one, and I saved the doozy for the end. You're like, 9 to the x equals 3. You're like, wait a minute. It's not a reciprocal. It's not a fraction to a whole number. So it's not a negative exponent. Which, nice, okay? Because you're like, well, wait a minute. What can I do to 9 to make it 3? Well, the square root of 9 equals 3. So how do I write the square root as an exponent to the 1/2? So for some of you, that part is going to be a struggle. Just kind of playing with this some. But again, If for the time being you have to write a list of cubes and squares at the top of your paper or have it sitting there, that's fine. But I want you to kind of work at this and make it a little more of a challenge to yourself, because it'll help you with the other exponent rules a little bit later too. But I'll come back to the calculator way of doing it later. I like you guys to think a little bit first. So when we're doing logs, there's two types. There's the common one, where if you just see something that says log of x, your little base number here is always assumed to be 10. Just like when you do a square root, it's assumed that it's 2. Or you do an exponent, you assume it's 1. So when you're doing these, there's no real easy way to take care of it. So we are going to let the calculator help us. So if you have not played with logs on the calculator before, there's a button for this. Over to the left, just about in the middle, below your squared button, there's this button log. Notice it already puts a parenthesis in for me. I'm going to type my number. I'm going to close it. And I'm going to get a funky answer. No, I don't want plus. Oh, dear. Timeout. Freeze. You are... All right. So again, I hit log here. I punch in my number because it already gives me the parenthesis, and I close it. You are going to get decimals on these sometimes, and typically we take them to 3 decimal places, unless you're told otherwise. If you're told to go to hundredths or thousandths, whatever it is, just be focusing in on what you're being asked for. But any log, if I don't see a little number down there, I can do this way. And these can come in handy for some things. Then there's this thing called a natural log. Now, that's going to be when we start discussing E a little bit more, and that's more towards our next section. But for now, there's also a natural log button, and it's right below log. It just says ln instead. So I still do it the same way. I just punch it in, and we're still going to keep going to 3 decimal places, to that thousandths place. So you do have to pay a little bit of attention as to what's going on to get the correct solutions on these. So that's one of our biggies. You're like, okay, this might not be too terribly awful. Then the story problem comes, and you're like, yeah, I'll just skip that. Don't do that, because some of you noticed on the homework check, I hit hard when the application problems get skipped, because those are the things that show up on testing issues, like ACTs and work keys and that stuff, so we can't afford to be skipping them. So the slope of a beach is related to the average diameter in millimeters of the sand particles on the beach by this equation. And again, slope of a beach is kind of important. You have big tidal waves and things coming in. You don't want to build a house where it's going to get knocked down. So again, it's an application that's legit. So here's our logarithm for it. Find the slope of a beach, so find S, if the average diameter, D, is 0.25 millimeters. So all I'm going to do is I'm going to do a quick substitution and plug in 0.25 for D. You're like, that's all? That's really all I got to do for that? Yeah. It doesn't mean just because it has some words with it that it's going to be something that's terribly difficult. Sometimes it's just taking the time to actually read through and figure out, okay, where do the numbers go that I'm being given for this? You're like, wow, that's not much of a slope. Well, you haven't seen a whole lot of beaches with a slope that goes like, this anyway. That'd be kind of crazy. People get hurt. So, like 0.78? Yeah. Not very steep. But again, that's where the connection part comes in. So you're like, okay, we've talked about going from a log to an exponent. We've talked about finding a value when they give it to us. We've talked about how to punch it in the calculator. What else can we possibly do with these? Well, we can do some things with inverses, opposites. Opposite of add is subtract. We've done that. Opposite of multiply is divide. We've done that. Opposite of squared, square root. We've done that. How does it work with logs? Well, let me tell you. There's 2 ways these can change. One of them is that the base and its log can, and in quotations I'm putting here, cancel each other out. And what I mean is if you have some log and its base and this are the same, it's like they're inverses of each other. They cancel each other out. So like for instance on 17, this log 6 and this 6 cancel, and all I'm left with is the exponent that's left. That's my answer. And I'm even going to be crazy enough to show you how to type this in on the calculator if you wanted to check me. Okay, 6 to the third power, I'll let you know, is 216. Here's how this works. Well, you're like, well, couldn't I just do 6 to the x equals 216 and figure it out? You could, but here's your other option. I cannot believe I'm showing this to you day one, but I'm going to risk it. You can always take the log of your big base and divide it by the log of your subbase. And here's what I mean with all of that mathematical mumbo jumbo. If you get stuck and you're trying to figure one of these out, if I take the log of the big number, remember to close your parenthesis or you're going to get all sorts of fun answers, and divide it by the log of your subbase. And this works on everything. You get the answer back. You're like, wait a minute. You mean I could have done that up here when you were driving me crazy with this stuff? I could have done like log 81 divided by log 3. Oh, I got to check, because if I can, oh, the greatest thing ever just happened because I now have a shortcut. I don't have to think. Remember, I warned you there's going to be a part of this when we get to a quiz that I am stealing your calculator. You have to know this. You have to work these out. I want you to use your brain or it will shrivel up. I'm serious on this. So try to do these when you run into these. Try to do them using your noggin. If you just absolutely are stymied, okay, you can go back to our shortcut, which is called a change of base. But again, whether it's the little number and the big one, or this way, where my log of 5 actually is an exponent, the same thing still happens. I can still cancel them out. My other inverse or opposites are E and ln. E and ln, whack. 15's all I got left. Now, we're going to learn more about this soon. This one I'm going to punch in my calculator. Let's see if we can discover how this one works. So E, when we talked about it before, is second ln, which makes sense. They're inverses. They use the same button. And I'm just going to type in what I see. So I've got 2 ln 3. And you're like, oh boy. And no, that is not 21n. It's 2 times the natural log of 3. You're like, why'd you do the extra parentheses? So my 3 only goes with the natural log, and then the 2 being multiplied, it gets all of this stuff in. You're like, wait a minute, it's 9. How can I turn that into 9? I'm going to show you a trick. You don't need to know this yet, but next section you'll learn it. If there's a value, if there's a coefficient in front of my natural log, that actually swings up and becomes an exponent on that number. You're like, wow, exponent to exponent to exponent. Yeah. E and natural log cancel, or are inverses, and then 3 squared is where the 9's coming from. But again, I can just put it on my calculator. I know. But if you understand where things are coming from, if you do something screwy sometime and get a weird answer, your answer, you'll be like, that doesn't make sense, and you'll be able to fix it. And that's what I'm really going to keep stressing to you. Now, this is the one that drives people nuts. I'm going to ignore the 5 for a minute. That doesn't have anything to do with what's going on here. ln and E cancel. I'm multiplying 5 times this. So when the ln and E cancel, this doesn't become 5 cubed. it becomes 5 times 3. That's where I've got to keep things straight between where my terms are. If there's a value in front, I have to pay attention to it. It's the little details. I know you hear that from me every section, but it's true. Here, what's the little number here again? What's my base when I don't see one for a log? Okay, 10 is. So this is really 10 to the log base 10 of 2. Oh, a number and its log cancel. And I get my answer. There even may be times that a number is in disguise in trying to trick you. The whole wolf in sheep's clothing thing. You're like, well, 3 and 9 aren't the same. I can't do anything. Is there a way I could change 9 into something that has a base of 3? 3 to some power equal 9? 2. Ooh. 9 is really 3 squared. Because when I turn that into 3 squared, ooh, the log 3 and the 3 cancel and just leave me what's left in the exponents. There's going to be a whole lot of manipulation going on, which some of you, I have a feeling, may be experts at. Maybe not in mathematics, but that's where we're going to try and kind of put our focus in with this. Okay. And again, this is like any other. It's going to take some practice and playing with to get better at it. Sitting back and waiting and IDKing and all that other fun stuff doesn't get us anywhere. It just kind of messes things up. Finding inverses, no different than when we did it with y and x before. You're like, now how do we do that again? Switch x and y. Solve for y. You're like, oh yeah, we used to switch them and then solve for y, and that would be, you know, my y to the negative 1. That's what I'm going to do here. I'm going to switch x and y. Ooh, solve for y. Wait a minute. If I'm solving for y, if I want to get this alone, how do I get that log 3 out of there? Eee, wait a minute. Let's see here. Log 3. What can cancel out log 3? Oh, wait a minute. That's right. If I have a number with the base, I can use its number. I'm going to fire a big term out here. Get ready. Sound like an English term here. We are going to what's called exponentiate. What? We're going to turn both sides into exponents. You're like, I can do that? Yes. Whatever that base is, I'm going to turn both sides into these exponents. Well, here's how that helps me. The 3 and the log of base 3 are inverses. They cancel each other out. What's all I got left over here now? Y. What do I have left over here? 3 to the x. Not 3x. The x is still an exponent, and I'm set. Because again, whether I've got something on these, whether I have a number and I use the log to get rid of it, so like if I have 3 and I use log base of 3, or like here, I'm trying to get rid of the log, so I exponentiate, either of those can work. And again, it's going to take some practice though. You're like, well, this is the same thing. I agree. What's the little number here again when I don't see it? 10. So what do I need to do to both sides? Once I switch these, look at number 24 as your example. Yeah, I'm going to take both of these and exponentiate them, because that's always going to be my base number. If they just have log there, we always assume it's going to be a 10 unless they put a number there instead. And so 10 and log base 10 are opposites. And if I don't kind of understand that, I can visually see that if I did 10 to the log 10 power, oops, did I do something bad? I put too many parentheses, didn't I? Yep, I did. Let's wipe that one out. I can kind of start to see, oh, and that 10 that's over here, okay. It kind of starts to work my way through these. So I can see that. But again, it's understanding the inverse. A number and the base of its log are opposites. ln's the same thing. ln's buddy, oops, move up a little bit, is e. So when I see ln and I want to get rid of it, I still exponentiate, turn everything into an exponent. Learn something new. You always thought you could just add, subtract, multiply, and divide. So those cancel. So I have e to the y equals, ooh, x plus 1. Oh, Harty. Silly man. You have to change the variables. Read your directions. All right. But y is not quite alone yet. You're like, so I can still do regular algebra stuff? Uh-huh. And I can get myself set that way. Now, think carefully, Harty. Think carefully. Okay, I'm going to do something smart. We're going to look at 27. I'll tweak a couple of things in a minute here because I want to take a look at one graph, but we'll get a little more in-depth with the shifts and things tomorrow. What I'm going to have you do is we're going to just take a look at a picture here because I want you to get a little bit of a preview on what this is going to look like. All right, so we've got log of x. All right, let's see what this looks like. Ew. Kind of looks like a square root function that's gone flat. Here's the things that I want you to kind of notice, though, with this. If I go to my chart, and this can even get a little, you're like, what's this error mean? It means the graph doesn't go that far. So you're like, okay, so I've got one at 1, 0, and then I got all these decimals, and then I see one out at 10, 1. So does that mean that if I hit graph, it looks like it just goes like this, and that's all I do? No. Because what would happen if I started to trace this is you notice, you're like, well, hey, it's still coming down here, but then it like disappears. Now, this isn't something I'd expect you to do on yours, but I'm going to change my table here so you can actually see what's happening a little better in your chart. I'm going to get back to where it gets near that error message, because what people tend not to see with this, they're like, oh, it doesn't just stop it. They go, it kind of keeps going, and then it gets to the error. So all of these are going to keep coming down and keep going. You're like, wait, didn't we just have something like this? Yes. With growth and decay, we had that wall here that it kind of hugged up against, but it never crossed. Now with logs, we've got that wall again, but now it's the y-axis that's acting that way. So don't just scribble a graph and go, oh, I'm stopping right here. It's got to keep going. So we have what's called a vertical asymptote. I like to call it a wall because my graph gets right up next to it, but it never goes through it. So this will always be, because you'll be asked for asymptotes, it'll always be x equals 0, because that's what this line is, unless, and we'll talk about this part tomorrow, unless you have a right or left shift. You're like, hey, it is. It's just the opposite of what we were doing. Because last time, the only time our range moved is if we shifted up or down. Oh, now it's turned into left to right when it's a log. Okay. My x-intercept is at 1, 0. We figured that out just from graphing it. And then transformation, and some of you left these blank on the quiz, and we talked about this. It's just a fancy way of saying shifts, but we're getting you into the math lingo here. There's going to be shifts on these? Yes, just like there have been on anything else. When something's going on inside of parentheses, and you'll notice like on 28 and 30 when we get there tomorrow, any of those numbers that are inside are my left and right shifts. But again, just like before, oh, that's the opposite one. So when it's plus, I go left. When it's minus, I go right. Yes. And then whatever's outside the parentheses, like this plus 4 or this minus 3, is going to be my up and my down shifts. So like for instance on 29 I go up 4, on 30 I'd go down 3. And there's going to be relationships with those in domain and range. Okay. Domain, here, remember it's my x values from left to right. I come up on 0, because I'm not going to the left forever. It kind of starts tailing down here. But I do go right forever. So there's going to be this connection between my asymptote and the domain. These values will be the same. My range, though, is the one this time that's the easy one. You remember it was domain was the easy one when we were doing growth and decay, because it was always negative infinity to infinity for domain. Now it is for range. Always, 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 always negative infinity to infinity. Never going to change, never going to change, never going to change. No, 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 no. And so all you're really going to have to do with these as you start doing them, Harty, you're going to try and get one in now, aren't you? Yes. Is if you have a difference with something, like the plus 1, because I know we wouldn't use the 5 minutes to get something accomplished, so I am going to get one more of these in. You're like, okay, so plus 1. Before I look at it, which direction is my plus 1 shifting? Left, because it's inside. If it was outside the parentheses, it would be up. So let's see here. When I graph it, oh yeah, I see it kind of starts to come over here now. So let me look at my chart here. And you'll notice now instead of at 1, 0, that point that was at 1, 0 before shifted left 1. Now it's at 0, 0. Before, where was my other point? At 10, 1? You'll never guess where it is now. Oh wait, I got to change my table set back. It is. Amazing how these things just happen to work when I understand. No. Why is this doing this to me now? Silly, silly, silly. 0. Let's try one more time here. That's why I don't mess with those very often. There it is, okay, at 9, 1. But remember, do not cut this graph off. It shifted my asymptote. Sometimes I like to even draw these in. Here's my wall. Now my wall shifted left 1. So my wall is at -1, and I come down. So these graphs are going to look the same. They're just going to move around a little. My domain moved left 1. Now instead of coming up on 0, I'm coming up on -1. Like, okay, moved left 1, the domain was. The range isn't moving, people. That's going to be the easy one on the next quiz. Range is always the same. My VA, my vertical asymptote, x equals, where's the wall at? -1. So I put it in there. And then my x-intercept, remember, is just going to be wherever y equals 0. At 0, 0. So here's kind of our outlook, depending on how pushy you want to get with things. We're going to do these last couple tomorrow at the start of class. Even right now, though, you are absolutely, positively capable of knocking out every question on this whole deal except maybe these last 3, because they're the graphing ones. Now, with the information you got there, I think you could do the graphing ones even. But for those 3, notice change of direction, domain and range, which is what the book says. But we're also going to look for the x-intercept and the end behavior. Like, ooh, end behavior, remember that. We're going to use that more as a review than anything else. But at the very least, everything before the parentheses you can do right now. And you notice this, it doesn't take that long. Any scientific calculator will have the ability to do logarithms. So you don't have to have a fancy one this time to make this work. Okay?